What I got, but I guess
Yes, but after the exam.
Okay.
my copy.
That's good.
I need to teach you a statistical analysis that you'll need to know for the AP exam, and we'll try to use on some of our data from our experiments. And that statistical analysis is called the ChiSquare test. Let me give you an example of how the ChiSquare test can be used. Here's a coin, right? Pay attention. What's the odds that I get heads on a flip?
1 out of 2.
50-50, right? 1 out of 2? Each flip is independent of all other flips. Doesn't matter if I get 4 heads in a row, the next flip will still have a 1 out of 2 chance of being a heads or tails, right? Now, suppose I flip this coin, and suppose I flipped it 100 times, and I got 50 heads and 50 tails. Would you think anything was wrong with my coin?
No.
No.
It's a normal coin, right? What if I got 49 heads and 51 tails? Do you think there's anything wrong with the coin?
No.
What would you say? Why am I getting 50-50?
Well, it's the chance.
It's not always going to be exactly 50% of the time.
There's chance involved here, isn't there? In the coin toss, there's chance involved. And the 49-51 result was probably due to chance, don't you think? What if I got 45-55? Think something's wrong with my coin now?
Not yet.
The difference is due to chance still, you think?
Yeah. Could be.
What if I got 40-60?
Still due to chance.
You think it's still due to chance?
Chance is blind.
What if I got 0-100? Think there's something wrong with my coin now?
Chance is blind.
It's possible.
Double tails.
Highly unlikely, but
If I flipped a coin and got 0 heads and 100 tails, you wouldn't think something's wrong with that coin?
I would.
I would.
Well, think about how many people are flipping coins all around the world. Surely someone's going to get 100 in a row.
There's a chance it could end up 0-100, but wouldn't you be suspecting something weird with that coin?
Yep.
If it did get 0 and 100?
Yes.
unless it was like really
At what point do we start suspecting that something is wrong with our coin? Maybe it's a weighted coin. You ever heard of weighted dice?
Yeah.
You know, this dice right here, what are the odds that I roll a 6 if I rolled it?
1 in 6.
1 in 6, right? You know what? It's been proven that that's not actually it. I rolled a 6, by the way. It's been proven that this die is actually not completely fair.
How do we know?
Because the holes were cut out in the dice. The side with the 1 having only 1 hole weighs a little more than the side with the 6 having 6 holes. And there's really slightly better odds of getting a 6 than a 1, because the heavy side usually goes down.
Is that on every dice?
Every dice that has holes cut in it like this. That's why they don't use these kind of dice in Vegas. They use die that are flat with the dots painted on. Those weigh a lot less. The paint weighs hardly anything. Isn't that interesting? And you can prove it statistically that you'll get more 6s than 1s if you roll it.
What if you have 2 die?
You got to roll it a lot to see the results. 2 dice gets a little more complicated.
Okay.
But we need some type of statistical test, some scientific way of saying when are the differences due just to chance, and when do we start suspecting that something is wrong? There is a statistical way to do this. It's called the ChiSquare test. And I'm going to show you how it works today. And we're going to do a little lab here where you use the ChiSquare test to see if your results are due to chance or if there's something wrong. Is that interesting? So you have to understand the ChiSquare formula. Look at this Lab 7 Statistical Analysis set. If you turn to the second page of it, you see the chi-square formula. You're going to have to know what this is and how to use it. Chi-square equals sum of observed minus expected squared over expected.
What is that? Curvy X?
That curvy X is the Greek letter chi. Do you know all the Greek letters? I can say them in less than 5 seconds. Alpha, beta, gamma, and sons, theta, theta, kappa, mu, psi, pi, rho, sigma, delta, phi, psi, omega.
Alpha, Bravo, Charlie, Delta, Echo.
I used to have to say those holding the burning match and say it 3 times to get in our fraternity house during Hell Week. I would light the match, then pause for effect before I start. That symbol right there means the sum of. Have you ever seen that in math?
Sigma.
It is. It's a sigma.
That's what I said.
Agreed.
Uh-huh.
Observed minus expected, in parentheses, squared over expected, is the way we will figure out if there's something wrong with our coin here. Instead of using a coin, let's use a biological experiment that you could apply this to. And here what they've done, if you turn back a page, starting the second paragraph here, or at the end of the first. For example, consider corn seedlings resulting from an F1 cross between parents that are heterozygous for color. A Punnett square of the F1 cross, big G, little g, big G, little g. Big G, little g, big G, little g, cross with big G, little g, big G, little g. We're going to cross that. Big G equals green. Little g equals albino. What do you expect to get? What ratio of kids do you expect to get here?
1 to 1.
Really?
3 to 1.
No.
3 to 1.
Have you ever made a Punnett square before?
Once.
You said it correctly. Someone over here. Was it Jessica?
3 to 1.
One, 2, 3 green to 1 albino. Who said it? Right. Yes. Y'all see? It's a 3 to 1 ratio of kids.
I just guessed.
When they did this cross, guess what? They didn't get 3 to 1.
Uh-oh.
They show you what they got on the bottom there. They got 72 to 12. And that's not exactly 3 to 1. And what you have to ask yourself, is this close enough to 3 to 1 to be able to just call it to 3 to 1, and the difference is due to chance? You see what I'm saying? So what you do is you plug it into the chi-square formula to see if this is close enough to 3 to 1. That the difference is due to chance alone. And we call that the null hypothesis. The null hypothesis says that the difference between the data you observe and what you expected to get is due to chance, to randomness. What numbers would we have gotten if it were exactly 3 to 1? It's a little math here.
24. 72.
We would have gotten 72 and what?
24.
Well, now we had 84 kids. So we got to keep the amount of kids the same. 72 plus 12, we had 84 kids. So if we have 84 baby seedlings, what is a 3 to 1 ratio out of 84? How can you figure that out?
63
63 over here
to 21.
to 21?
You do 1 over 3 equals 63.
Is that right?
Divided by 20. Yeah, that's it.
Does 63 plus 21 equal 84? Is 63 and 21 a 3-to-1 ratio? Emery, were you on state championship math team?
No.
That was good. You just did that in your head? How'd you do it?
It's 84 divided by 4, because there's 4 parts.
She said 84 divided by 4 is 21.
Why'd you do that?
Because she was trying to figure out what a 3-to-1 ratio would be.
Because there's 4 parts together.
So there's 4 parts. 3-to-1 ratio is 4 parts. 84 divided by 4, that means there's 21 each part. 21, it should be 21 recessives, and 3 times 21, or 63, dominants.
Oh, okay.
Good job. That impresses the former state championship math team, doesn't it? So this is what we observed in our experiment. This is what we expected. And those are the numbers you plug into the ChiSquare formula.
Let's do it.
So, here's how you do it. Fill in this chart here. Observed, expected, and then let's do observed minus expected for each possibility, for the green possibility and for the albino possibility. So you write down in your chart, observed, 72, expected, 63. What's observed minus expected?
9.
9.
Nailed it.
Are y'all writing this in your chart? It's exciting, isn't it? Savannah says it is.
Oh, wait, this is the wrong page.
The 85 of the handout here?
86.
I'm on 85. Well, you can do it on 86.
Yeah, the
There's
same
another
chart.
It's the same chart, only more advanced.
Okay.
Yeah, let's do it on the chart on 86. It's the same chart, only more advanced.
Okay.
So observed was 72, expected 63, observed minus expected is 9. Observed 12, expected, how many?
Oh, whatever.
21, what's observed minus expected? Negative 9. But the chi-square formula uses observed minus expected squared.
What? Sigma? 81.
Sigma means the sum of. I'll get to it in a minute. Actually, that sum of symbol should be on the side right here.
Uh-oh, that's not good.
It should be the sum of all of that. So, what's observed minus expected squared for both of those?
81.
81?
Mhm.
9 times 9?
Uh-huh.
You could use a calculator to do this if you wanted to. And then you have to figure out the observed minus expected squared over the expected.
81
What's
over
81
63.
divided by 63?
I got a calculator.
So,
9.
the first fraction will be 81 divided by 63.
Which is 9/7.
81 divided by 63 equals 1.28. So observed minus expected squared over expected, you write 1.28 in that column. I'll write it here on the board. 1.28.
So you don't want fractions or decimals?
No, never use fractions ever again.
Really?
Yeah, please.
Okay.
Don't. And what is albino observed minus expected? Squared over expected. 3.86? What was the fraction you used to get that? 81 over 21,
27/7.
which is 3.86.
Wait, why'd you do 81?
Because observed minus expected squared is 81. Right? Over expected, which is 21. We expected 21. Right?
So you got 3.2.
The 3.86 plus 1.28. Can you add those together? That's what the sum of means. The sum of means you add the two, you add the chi-square value for green and the chi-square value for albino added together. That gives you the sum.
5.14.
5.14.
Championship calculator team.
You then take that number. Everybody with me so far?
Mm-hmm.
You take that number and you compare it to this probability table below. We're going to operate at the value of 0.05 probability. That's 5% probability. And most science works at the 5% probability level. And the next thing we have to figure out is what's called our degrees of freedom. Degrees of freedom is a statistical term, which basically all you do to figure the degrees of freedom is you count the number of possible outcomes, the number of groups you had in your experiment. How many groups do we have in this experiment?
Two.
Two groups, a green group and an albino group. And we subtract 1. So 2 minus 1 is what?
1.
Are you with me, Emery? You can't lack paying attention here. 2 minus 1 is 1. So for this table, you use the 1 degree of freedom. And what number do you see under 0.05 probability?
3.84.
3.84. Are y'all with me?
Nailed
Why'd
it.
you do 2 minus 1?
Because there are two possible outcomes here. You can either be green or albino. And to figure out your degrees of freedom for this calculation we're doing, you got to subtract 1.
Why?
Well, you ever play musical chairs? Yes. Ghosts in here. You ever play musical chairs? You know how there'll be 6 people and only 5 chairs? So those 6 people have 5 degrees of freedom. There's 5 places they could sit, but there's 6 people. You subtract 1 to get the number of degrees of freedom. It's kind of like the number of chairs left in the musical chairs. If you have 2 groups, you basically have what's called 1 degree of freedom. There's only one. It's got to be either this or this. If there were 3 groups, there'd be 2 degrees of freedom. It could be this or this, or this or this. There's you don't have to worry about it. All you got to do is take the number of groups that you have and subtract 1. Okay? And I'll show you how to do this. We're gonna do several examples of these. But see our number that we're looking at is 3.84?
Uh-huh.
If this number that you got for a chi-square value is less than that number in the table, that means your results were due to chance alone. The difference in your results and the difference in the results you observed and the results that were expected were due just to chance. That's if your number is lower than the number in the table. Was our number lower than the number in the table?
No.
Our number was higher than the number in the table. Are you with me here, Savannah? So, was our data our difference here? We observed 7212. We expected to get 6321. Was 7212? Would that be just due to chance alone?
No. Because
Not.
it's greater.
Something's going on in our experiment. Something's different about the inheritance of these genes in corn. At least that's what our statistical analysis showed us. Maybe corn doesn't, maybe their genes don't split up really nice like in Mendelian genetics. Maybe their genes are linked or something like that. Because we're using the 5% probability, what we're saying is there's less than a 5% chance that we get these numbers 7212 if it's supposed to be a 3-to-1 ratio. Less than 5% of the time will we get numbers that high for our.
Did we use the 5% because that's the number?
You usually use 5% when you're doing an experiment.
They give this to us.
They're going to give you these tables,
that we used?
but you'll have to be able to use the data.
Okay.
2 minus 1.
I want to do a little experiment now where we do the same thing, but we're using M&Ms. Do you like M&Ms?
Yes.
Well, you're going to get to eat M&Ms. Why don't, even though you're with this person, why don't you take your own
No,
package?
this is actually a level
compare
concern.
it with them.
Do I keep filming?
Yeah, you can keep going.
Okay.
I'm supposed to not forget us.
Oh, they're not,
Okay. Here's the deal. M&Ms come in 6 different colors. Do you think they just pack these things randomly with the M&Ms?
Yes.
Or do you think they pick, I'm going to put more reds in this one and more blues in this one?
Random. Well,
Okay, that'll be our null hypothesis, that they pack them randomly. But maybe they don't.
We should test it.
Let's open our M&Ms. Don't eat them. Oh wait, let's put them on paper towels so we don't have to deal with dirty desks. Everybody, come get a paper towel. Put your M&Ms down on a paper towel and separate them out by color.
is this the one that we're doing in our logbook? This experiment?
Yes. Write this down in your logbook. What you're doing. Separate them out by color. Put all the blues together and count them. Put all the reds together and count them. And write down your results in your logbook.
I think I can film the M&Ms.
And I'll tell you what we expect to get. You got to count up the total number too.
Can I wash my hands first?
In other words, yeah, make a chart. In other words, make a chart. Just like the chart that they made here. Put all the different colors. Put the number observed. And then we'll figure out the number expected. Use this chart as a guide. I have your lab book. Here you go. Woo. Look at all your blues.
And you want us to write out what we're doing?
Yes.
So what we just label this lab 7 right here?
This is ChiSquare. ChiSquare test.
Okay. So let's do red, orange,
Today is Wednesday the 17th.
Roy G. Biv.
Yeah.
What kind of chart should we do? Should we do should we just do the red number or
Yeah, just like this.
just like which one?
Color, red, blue, green, and so forth. Number observed, blank. Number expected.
Okay, so phenotype, color, then I see. So
I film some M&Ms until we figure this out.
red 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 reds. Yellow. There are 2, 3, 4, 5, 6, 7.
Hey, real quick, Mr. Willis,
Nine
yellow.
what would we say the purpose of the lab is? Figure out the M&Ms?
Statistical analysis.
Okay.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Blue, brown, green, orange, red, yellow.
11 orange. What color is that? Is that brown? Black? What color do you call that?
Brown.
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 Okay.
Blue, brown, green,
5,
Orange.
5 green.
red, yellow.
Blue. First column, that's number observed.
2, 4, 6, 7 green, 4 red, 2, 5, 6,
I'm just gonna call it
9 yellow,
O.
8 brown, and then
Okay. So we got it as a percent?
Well,
Or, so I have 10, 9.
sweet scale orange.
I just counted them. Is that 10, 9?
let me let y'all in on a little secret. The M&M's company has told me through the magic of the internet that these are the percentage M&M's that they put in their bags.
Red and brown.
Now, how many total M&M's did you count?
54.
You counted 54 total M&M's?
Uh-huh.
Did everybody get 54 in their bag?
10 plus 9. Still is. You're cheating.
I've already done this stuff.
Okay.
Because of the absent people.
Some extras, yeah. So this come out of the...
You got 55 total?
We got an extra one. Can I eat it?
No.
55.
You got 55 too? How many did y'all get, Dante?
5.
We're still going.
Y'all got 55?
5 green,
Sounds like people getting 55.
7 brown, 1.
Let me ask you something. Those of you who got 55 or 54. If 24% of your M&Ms
54.
are supposed to be blue, how many blues should you have in your bag? You had 55 total. How could you figure that out? You got 59 in your bag? That is an awesome bag. Let me ask you a question. If you have 59 total, but 24% of them are supposed to be blue, how many blues would you expect to be in your bag? Do it. Figure it out on your calculator. Figure out your number of expected.
We got 56 actually.
12.1.
Okay, if you have 56 and 24% are supposed to be blue, how many would you expect to be blue in your bag?
I got 12.1.
Okay, write that down.
So how do you find the expected? You multiply the percent by the number you got.
Yeah.
So 0.24 times the number of blue. Right?
No.
No.
0.24 is a percentage of blue. 24% should be blue.
Right,
1/4 of them.
So,
about.
so how do I do the math? I just
Well, think about it. What's your total number?
blue is 12.
No, total number of M&Ms.
54.
There's 54.
Mhm.
24% of them should be blue.
Blue. Okay.
So how do you figure out how many should be blue?
13.4.
54 times 0.24. Okay.
Can you do that for each of them?
13.44. 56
Is what?
is 24%.
Are blue?
Yeah.
Yes.
How many should have been brown in your bag?
Just do, what I would have done is multiply 0.24 and 55.
What do you need? You don't have a calculator?
Yeah. This is biology.
Uh-huh.
12
I know, Emery's got a cell phone.
times. You were supposed to look. I brought my calculator because
Good
I
job.
always carry it with me.
7.28.
So, do we round to the which place?
You don't have to round.
No.
7.28.
Even though there's no such thing as a 0.4 M&Ms, unless one was broken.
0.48.
Let's just leave it at one decimal place.
7.3
So 2.9.
brown.
Okay, how many green?
I'm just gonna leave it up
You see what I'm getting at here? Jessica,
8.9.
are you writing this down? Would you want to do it for every one of them, you think?
8.6, right?
Would you want to find out the expected for every one of them?
You round that down to a 6, right?
Keep going.
Blue.
Y'all know what you're doing here?
Oh, we got 57.
We got 105.
That rounds up to
In what, in that one bag?
13.0.
Holy
We got
crap.
11.
Yeah, we're really
We
digging
did it
it.
like 12 times.
11 ones.
We got 11.
That's an unbelievable bag.
Yeah, look at their.
Let me see your bag.
They got like a.
Oh, you got a sharing size.
Oh,
Your
there.
bag.
I was about to say something.
Whoa!
Can you guys figure out the expected?
Oh, come
I don't
on.
want to share this out.
You know how to figure out the expected? Caitlin, you know how to do this? Now, do the ChiSquare formula.
I have a question. Mr. Willis, give her a calculator.
There's one on the lab table, the head table in the lab room.
How many did we get total?
You write down your observed.
So we just timed.
Jessica, how many did you observe?
How many do we
On
have?
blue.
Of blue. 14.
Okay.
And that's actually wrong
Yellow is
because
14.
we didn't have 14 left.
Red is
So, observed minus expected.
It's actually 13 point.
Observed minus expected squared. Observed minus expected squared over expected. You should do this math.
For the E, it's supposed to be 13.68.
Okay?
so.
Can I round to 13.7? That's pretty close.
Make sure it's not
We got 3.
I feel like I'm not doing anything.
So observed minus expected is 0.3. Observed minus expected squared is 0.09. 0.09 over 13.7.
That's what we're observed. We got 5, right?
So our negative's okay?
Yeah. Well, no, the negatives, when you square it, the negatives are going to
Oh,
disappear.
yeah, you're right. So,
Yeah.
5 minus 6.
Will you real quick, Isaac, do this for me? 0.09 divided by 13.7.
Divided by 13.7. That is 0.006569. 6569. Or 9 over 1370.
I got it.
Okay.
What do we do after we?
I can
Have
graph
you
that.
figured out your observed minus expected squared over expected? That's your chi-square value for each one?
For each color.
For each color? Have you done that? Have you figured out your expected for your blue M&Ms?
The amount I'm supposed to get? Yeah.
Did you figure out your expected for your brown M&Ms? So you figured out all the expected. And you know you're observed because you counted them, right? Have you done observed minus expected for each color? That's what you need to do. I only have 3 M&Ms left.
Do you have another calculator?
Huh?
Do you have another calculator?
There's one on the front lab table in the lab. Did you get it? Oh, she got it. Oh, yeah, I do. Look.
We had answer 29.
Calculators.
Okay, all done.
Did you get a chi-square value?
Not yet. Almost. I just squared them, but
You got to add up all these, and that'll be your total chi-square.
uh-huh.
Because it's the sum of observed minus expected squared over expected.
Uh-huh. So if are we rounding to the nearest tenth? Or I did.
Yeah, that's fine.
So if I have 0.04, would that be just 0.0? To round?
Yeah.
So 0.0, okay, just to round up or
Who
round
figured
down.
out these equations?
You can derive them. They're derived from percentages. If you want to figure out what's 5% chance that those numbers don't work out, you can derive the equation.
So you just anyone can come up with it.
You can come up with it if you know math well enough, yeah.
1.3.
That's how all equations are
Yeah.
made.
The
They're derived
Pythagorean.
from something we already know.
1.4.
No, I'll just get it.
0 over 10.8, is that 0? No. 36 divided by 13 is 2.8. 13 over 8.6.
Anyone getting close?
1.5.
It's okay, Brian.
82.8 over 2.9. Okay, right. It's 28.6.
Wait, hold on. If we were expected to have two 13%, why would we have one 4.9 but not the other one?
What are you talking about?
For the
Just round
expected.
to a decimal place or two.
Well, because we have observed.
I know, but like the expected. How many do we have?
We multiply the expected percent times 54 to get that value. So I think it's right.
I know, but we had two 13%.
We had one.
We had two 13s.
Oh shoot.
Brown and red.
Because Mom, I wrote it.
Brown. Where's brown? Put brown as 24%. That's wrong. That's wrong. That's wrong. That's wrong. I just messed up all my data. Sorry about that.
No.
Yeah.
I caught
Because I was
something.
ambiguous. Brown and blue both start with B.
So 8.6
We had
for red and brown.
13% brown. Oh shoot. Well, we observed 7, so I have to erase this column. It's okay. It's not the end of the world. Just erase this column. Or row. So.
But everything else is
4
correct, right?
13.
What'd you put for yellow?
7.7. Observed minus expected. Okay, that's 0. Observed minus expected squared, 0 squared is still 0. Over 0. So observed minus expected squared is 0 over anything, it's just 0. Is that better?
Should be.
I was just ambiguous
Just
about
add all the percentages up to 100 once you get those. Or I'm sorry, not all the percentages up to 100. Never mind.
So add those up. So add
Red
1,
Hold on.
2, 4,
Yeah, once you're done, you can eat them.
3 plus 3 point. So we just add up all the columns, our last column.
That's right, you add up all the columns.
Plus 1 point.
How many degrees of freedom in this experiment?
5.
Savannah,
So the sum.
how do you know there's 5 degrees of freedom? 6 minus 1 is 5.
Which one's blue?
You go to your table under the 0.05 probability. 5 degrees of freedom, what's that number? 11.1. If your number
Blue's
is
24.
less than 11.1, it's just by chance
Real quick,
that your M&Ms in your pack are off.
if blue is
from what
24%, why do we only
you
have
would expect by
2.9? It's the
random.
largest percentage.
From what you would expect. Was yellow's less?
12, we have 12 blue.
Then 11? Yeah. 0.1, it wasn't?
24.
What was it?
54 times 24. 0.24 is 2.9, I think.
Maybe they aren't packing these random.
124 times 54.
I copied the wrong side.
Which one was up?
12.9, okay.
Well, it'd actually be 13, 13.0, because you round up.
Okay, we'll just,
Oh wait,
13.0.
7.2.
Darn it.
What was that one?
and then green,
We're 5 degrees, yeah.
16%, 8.6, that seems about right. Oh, hold up.
Oh no, oh, green is 4. Yeah, no, yeah.
Brown was what
Maybe they
percentage?
aren't packing these random. According to
What
your
percentage is
data,
brown supposed to
they
be?
aren't randomly packing these.
We should assume that.
1.
That means you would reject
Brown's
the
supposed to
null
be-
hypothesis.
Brown
Observed.
got the same percentage as red, okay.
So 113.
Yeah, you can eat them after you're done. What'd you get?
Is
That's less than
Point.
11.
Where are these?
So you accept the null hypothesis. The difference between
Point
your
one.
data and what you
0.1.
expected is due
Oh wait,
to
we're done here.
How do you
We're going to continue on this
what
Friday.
do you do with this though? Once you get the summer?
You add all these chi-square values together to get the sum of them.
Alright, we're done.